In the last class, we talked about the parallel transport equation, or the idea of parallel transport, in which we said that a vector can be parallel transported. Let's say it's a two-dimensional curve, then a vector can be parallel transported by moving it infinitesimal distance along the curve, which is parameterized by lambda, and moving it to the end of the curve. Now, if it's a two-dimensional curve, then the initial vector and the final vectors are going to be parallel of the same length also. But if it's a 3, I don't know how to draw 3D, 2D on 3D, but let's assume this is 3D. In that case, the curve will not stay parallel to itself from the initial vector is not going to be parallel to the final vector, but any two subsequent vectors very close to each other, when parallel transported, will remain parallel. So this is parallel transport. Now the equation we obtained was dv mu over d lambda plus the Christoffel symbol alpha beta v alpha dx beta divided by d lambda equals 0, and this was equivalent to dv over d lambda, that there should be no change in vector vector v if we change the lambda a little, and this is called the covariant derivative. Now there's nothing like contravariant derivative. It's just the name covariant derivative. This sort of confuses us, because this has nothing to do with the covariant and the contravariant vectors. It is just the name. I think it has some historical reasons to be named like this, but I don't really remember. But this is what is called the covariant derivative, and this is actually a common thing. It's used in fluid mechanics. It appears very often. Okay. So, given a closed loop in 3D, the curve does not come back to its original orientation, but 2D it happens. If you go along a closed loop, then the initial vector matches the final vector, same as what I explained before. I mean, for these two cases. Okay. Now there's an important property which we will discuss, is called geodesic, that instead of parallel transporting a random vector, let's parallel transport the tangent. What does that mean? Which basically means if you have a curve, you have this tangent, and you parallel transport it, and it comes here, and then as you parallel transport, you have this new tangent. Now I hope it's clear. So you have, let's make this long d lambda. This is actually long, so I'm going to exaggerate it, something like this. Now it doesn't really look, it's a tangent here because I have made my lambda too big, but just to show that the transported vector, or tangent, is parallel to its original tangent. Now this will not happen for any curve. You can parallel transport any vector along any curve given it's smooth, but this will never happen that for any curve the tangent, when parallel transported by d lambda, stays parallel to its initial um, tangent. It's going to happen only for certain types of curves. For example, in 2D, we all know what does a parallel transport, I mean, what kind of curve will satisfy this kind of condition. We all know this will be a straight line. So if you parallel transport from here to here, we know the tangent is the line itself. So if you parallel transport the tangent, which is let's say looks like this, then you again like this, and then again like this and this. Keep parallel transmoding all in the same direction, and you see that all you get is actually satisfies this condition here. Well, the condition is this, that instead of v, now we are actually talking about d x alpha over d beta. As a matter of fact, this equation will become d square x mu over d lambda square. Oh, sorry. This is d lambda plus mu alpha beta. This is going to be dx alpha over d lambda and dx beta over d lambda equals 0. So I've just replaced v by the tangent vector. Now this is not going to hold true for any kind of vector, any kind of curve. It's going to only hold true for certain curves, and these curves are called geodesics. You see, for two-dimensional plane, it's always a line. It's a line. Is this property of the coordinate system, or is the property of the geometry? Well, it's the property of the geometry, because now we see the geometry we are considering is a plane. It's a plane. Well, you may recall that for a sphere, the geodesic is nothing but the latitude or the longitude of so you have to some point 1, point 2. When you connect them, the geodesic is nothing but the latitude or the longitude, whatever you call it. It's called great circles, which go all around the sphere. So this is a geodesic. This geodesic is going to satisfy this condition. It's difficult to see for three-dimensional case, but here it's very easy to see. So in this case, we see that the geometry is confined to the surface of the sphere. So it's geometry dependent. By the way, does geodesic change as you change the coordinate system? Well, it should not change as you change the coordinate system. Let's say instead of using Cartesian system, you start using polar system. Will the geodesic change from a straight line to something else? No, it will not, because it's the property of the geometry. One way to see it is that you can, well, there are many ways you can actually prove this. One way is that this equation can be derived by something called action principle, and I'll certainly talk about this later. By minimizing the action, you get this equation, and this action principle does not depend on choice of coordinate, does not depend on choice of coordinate system. And from there we can see that actually this really doesn't depend on the coordinate system. Now as you can see, geodesic is a property of the geometry, so it will play a role when we'll start talking about space-time geometry produced by the masses, because we know that mass curves space-time. So then it will be useful to understand. So basically this is basically everything leading to the idea of curvature, which we will probably not talk in next few lessons, but later. Next class I'll probably talk about how how geodesic and equivalence principle are related, or how they mean in together.